You should be able to see me scribbling here. Okay, GANs. So what are GANs, right? So remember, our story so far was that we have some probability distribution, okay, and we have no idea about this, okay. But what we have is we have a bit of data, okay. So what do I mean by this? Take any example, okay. The simplest, the most the example that will clearly relate to is human faces, okay. Now, if you look at all human face let me say photos, okay. If you look at human face photos, then that's a data set we can easily understand what it is. And if I show you photos of, you can almost realize that either it's AI generated or not, right? Now, 10 years ago, this GAN that came out and subsequent improvements that happened in a couple of years managed to come up with photos where it was slightly difficult to realize whether it's AI or not. Okay, so I think there's a website called this human does not exist. Okay, this person, sorry, this person does not exist. Okay, all right. So, but if I show you now, right, it's probably impossible for us to really believe that it does not exist. Okay, so and this was again, we are still like 8 to 10 years back in history. We are not even talking about the diffusion models that are the current state of the art for image generation. So GANs managed to do this. 2014 it started, but by 2016 it became very good. Okay, 2016 to 2018 was a very big boom of GANs, and then eventually diffusion would take over. Okay, so probably today it's not as relevant in most problems out there. Nevertheless, the idea behind diffusion, VAE, GAN, they're all the same. The common idea is that you have no idea about a distribution. Not only do you not have an idea, you can never get an equation for it. Okay. However, you do have access to data. Okay. So the point now is to estimate it. And so far we've been doing exactly that. We have been coming up with techniques to estimate it. And in the VAE thing, we had some sort of p theta of x, and we wanted to minimize its distance between these two, or let's say KL divergence or whatever it is between the original data and the estimated data, where theta came out to be some parameters of autoencoder side architecture, right? Today we'll kind of follow along that track, except that we will not directly look at this as a maximum likelihood or a KL divergence kind of angle that we had there. Okay. What we'll instead look at, we'll look at the geometry of what's going on. Okay. And very often,
Ajay,
sorry.
there's a suggestion to use thicker pen. I think some people cannot see. Can use a thicker brush slightly.
Okay. Cool. Cool. All right. Is this good? This is fine, right? Okay.
Yeah.
All right. So we look at the geometry. Okay. And this geometry, again, the idea behind this geometry is still very similar to what we saw in the VAE example. We'll continue to see that. And I won't assume that you have been through our VA lecture to follow this. Okay. So it's okay even if you skip the last two classes, you'll be fairly comfortable today. Okay. So the idea is the following, that you have some distribution. Okay. And whenever I write a distribution, I generally put some cross marks everywhere, right? Okay, and that's our idea of a distribution. This is a two-dimensional distribution, and any so what does, these are points that are typical of the distribution. Okay, for you to believe that a new data point belongs to this distribution, it shouldn't be in far off places here or here, right? If it's far away, then you know that it's not coming from that distribution. If it's nearby, you tend to believe that it comes from that distribution, right? That's the most fundamental aspect of all these generative algorithms. Okay, now the goal right now is that this x here came from your p data. Okay, let me just for a moment switch over to Goodfellow's notations. Okay, otherwise it will be a little.
Write a speed data.
He writes p data and p. He doesn't really write a p theta per se, right? So we don't need p theta in these notations, but p data is what. Yeah. Okay. So he uses this notation. So the goal of this lecture is that after this, you should be able to go back, read that original paper and make sense out of it. Okay. So he calls this x coming as p data of x. Okay, and in our mind we can think of images or something like that. Now there's another distribution we bring in, again very similar to our VAE setup. We bring in z coming from what he calls pz. Okay, pz of z. Okay, and this is typically a standard Gaussian, 0 comma sigma squared I. Okay, this is a standard Gaussian. Now if I look at samples of z, they will typically be in the vicinity of the origin, where our intuition of a Gaussian we already know, right? 3 sigma rules, all those things that we saw. This will be now contained inside a circle of that shape. Okay, so if you look at there'll be it's in one dimensional, we know. In two dimensional it'll end up being circles. Okay, so most of the points are in and around the origin, and if you go far away, then number of points will be lesser and lesser, and beyond the 3 sigma you'll almost never see points coming up, very rarely. All right, so this is how a standard Gaussian is. Okay, now the goal of this lecture is to come up with some sort of a function that maps these z to our x points. Okay, very crudely I'm writing here. Okay, it meaning it takes us it so the idea is this: the function f of z should take this function take this z and map it to some x. Okay, and this x should be similar to our p data, similar to p data. Okay, that's the goal. All right, now while VAE had a lot of math, lot of um, maximum likelihood, KL divergence, all those things that came out, this luckily for us, GAN has a nice geometry. Okay, and this geometry is nothing but a classifier. The first thing we have to understand is a classifier. Okay, and this helps us once you understand what a classifier, we already know what a classifier is. We've seen logistic regression kind of a thing, we've seen neural networks, and in that we have a decision boundary. So classifier has a decision boundary. We'll think of a simple binary classification here. Okay, so what is this decision boundary? To do a quick recap, if you have a bunch of points of, let's say, let me use a different color here. If you have a bunch of points that are, let's say, blue, and a bunch of points that are yellow, right? The decision boundary that we want is something that can put things on both sides. Okay. Now, whether it's in this case, in this case, a simple logistic regression works. Okay. So logistic regression works. Okay. Or even a neural network works. Both are fine. All right. The fundamental thing that we have here is that we have two kinds of classes. This is class 0. This is class 1. Okay, we have two kinds of classes, and whatever, like for example, when we had even seen this TensorFlow playground, right? Right. Notice that they have two colors here, and when you run this, you'll get this decision boundary. Okay. The challenging factor now is that, can I still get a boundary that is almost like this, but we don't have a second class? Okay, that's one aspect. So there is a classifier, and the technical term I'll be using for this classifier to be consistent with the notation that is there in GAN literature is that we're going to call it a discriminator. Okay, so whether in today's class, whether I say discriminator or classifier, imagine that they're the same. Going forward, will only be, I mean, whenever you see GAN literature, you'll only see the word discriminator coming up. Okay, the goal of the discriminator is to distinguish whether it's a real sample or a fake sample. Right now, we imagine we have a folder with all our face images. Okay, and they are only the real data. Okay, so for us, let's say class 0 is real data. Okay, fine. So our goal is to come up with some sort of a decision boundary, some sort of a tight decision boundary, where if it's a face image, it says yes. If it's something else, if it's a dog, let's say human face, okay? If it's a dog or a table or a computer or whatever it is, then it says no. That's it. Okay. So here, in our data set that we want to imagine here, we have human faces. Okay, human face. And here I have everything else. Okay. So So this is real data. In our case, class 0 is real data. In our case, human face. Okay. And class 1 is everything else. Now, can someone tell me, is this a simple problem to solve? Everything else. Can I simply give a bunch of human faces and a bunch of non-human faces as my data to train a classifier to get a nice decision boundary around human faces? Is it possible? Should look
Yeah,
simple. Yeah, Yogi?
yeah, it is possible, right? I mean, like
No,
simple face recognition in a way, or
Yeah.
simple image recognition.
You just have to mention whether it, so the algorithm should simply say, is this a human face or not? Looks fairly simple for me. What do you feel? Anyone else?
I don't
Method
think so that it would be this easy or this simple. The reason being, the ground truth or the human face class in real would be a quite a big real data. Like it's like the distribution that we don't know, right? We can only assume that we can only give couple of different scenarios, maybe bald hair, maybe
Ah,
uh, any other, but
yeah.
we
Let's say you have 1,000 samples of bald people, 1,000 samples of spectacle people, so all different races, height, whatever, everything, right? Gender, everything that you have 1,000 samples of all, and you have like tens of thousand, maybe a million samples. Okay, does that solve
But
your problem?
would it not depend on what the non-human faces are? I mean, you're if it is a simple problem, you're fundamentally assuming that the non-human faces are very different than human faces. What if it's
Which
a
is
human
true.
and a chimp, or a human and a monkey, or whatever, which sort of comes close to each other, right?
Okay. Okay. All right. Okay. You're saying that there might be something that's very close to these boundary points, right?
Yes.
Yeah. There may be primates that are not human and may still look humanish, right? As compared
Exactly.
to as compared to different animals, like let's say snake or something. So snakes will be far away, whereas primate, gorilla, chimpanzees may be quite okay. That's a reasonable thing to argue out in the beginning. Okay, anything else? I'll also monitor some of the chat messages here, right?
No, not much, I think.
Not much in the chat. Okay.
But you said
Uh,
real data, right? Real data means real human faces, right?
real human faces. That's what I mean.
There can be fake human faces in everything
No,
else.
no. For now, just imagine human
Okay.
faces. Okay.
Okay.
Let's assume there are no fake human faces right now. Just there are human faces, and I want to mimic it. Okay. I want to mimic that. So the challenge is that, see, there are two things that are going on here. Okay. First, so let me write down two important points. My first important point here for me is getting a tight decision boundary. What do I mean by a tight decision boundary? It is basically going to tell you, it is going to give you a 0 or 1, right? Meaning human or not, human face or not. And it should be very accurate. Imagine a perfect classifier that will always give you a 0 or 1 based on whether it's a human face or not. Let's say. Second is, suppose, like now I put it, suppose 1 exists. Okay. That is another chain of thought that we're going to go for. Okay. Suppose 1 exists, what are the steps I can do? Okay. Step 1, step 2, step 3. I can do a few things if 1 exists. Okay. So there are two things that I'm going to talk today. And when both those things are something you truly understand, the GAN architecture reveals itself very nicely. Okay. That's the goal for today. All right. Okay. So let's spend a little more time on the tight decision boundary part. Okay. What are the challenges? So many of you are getting some sort of intuition there. Okay. The intuition says that, okay, everything else, how do you properly quantify everything else? Okay. Anything else you want to tell me about in terms of human and not human? If I can get enough samples of this side, then can I get a tight decision boundary? So you all get what I mean by a tight decision boundary, right? No matter if it means slightly deviate from human face, it should say no. Just like this here is an example of a very tight decision boundary. If I go a little away, it says, no, not a blue point, right? Something like that. Okay. Anything else? Any other comments about this? Mridul, right, need not necessarily mean overfit. Okay. It's something like this, right? It shouldn't be, okay, I get where you're coming from. It shouldn't be very tight where the decision boundary has unnecessarily curves like this. Okay, let's not go to that extent of tightness here, but in the general region. Okay. Well, let me continue the story. Most of you got this right. In this everything else here, okay, there is a big problem. Okay. Why? Because remember that any sensible photo that we've been taking, imagine all the photos that all of us have taken. Okay. So here's the data set I'm going to talk about. Okay. All photos that all of us, all humans across the last how many decades that photography has been around, and even you can even bring in paintings of older artists and all that, right? All photos, drawings, paintings, okay, of all humans, right, ever taken. This happens to be a very small, to use Shrikant's word from last class, manifold or subset. Okay, I may write manifold here if needed. Okay, manifold, very small subset of all possible images. Okay, why? Because think of something like you have a 10 megapixel camera. Okay, how many photos can you make out of that? Right? Each pixel, each value. So when you say something like 10 megapixel, okay, what you have is you have a red, you have a green matrix, and you have a blue matrix behind it. Okay, RGB. And if you look at the megapixel numbers, can we? Is 1 megapixel exactly 1 million? 1 megapixel resolution.
Should be some 1024 or something, no?
1024.
1 million. Okay.
Yeah.
Okay. Megapixel is 1 million pixels, I guess. Some approximation, but whatever, right? So even a 1 MP. So by the way, I don't think anyone has 1 MP cameras today, right? I'm sure. So yes. So probably 10 megapixels or some 10, 20, 30, whatever. Okay. But even if you rescale all the images that I mentioned here, right? If you rescale all images taken by humans into 1 megapixel, okay, how many are there? How many images can you make? Well, each of these slots can be filled in 256 ways, right? So it is 256 into 256 into 256 like that. Okay. To the power what? 3 million, right? So it's essentially 256 power 3 million. Why 3? Because RGB, right? Each pixel has 3 values. Okay. So 256 power 3 million. Can you even imagine this number? Okay. Even if you think of 100 power 3 million, forget 256. Okay. How much is that? Is it 10 power 30 million? It's a 30 million, the number of digits. Imagine a number where the number of digits is 30 million. Okay. We don't even know what that is. Okay. And that is just for a 1 megapixel camera. Okay. And as you keep increasing to your current photos, then the number of digits of that number of images you can make is so large. So all human photos that you can put is extremely small. And this is exactly what Shrikant was talking about last class, that there's a very small manifold on which actual images lie. And the beauty or the complexity of these algorithms is to go and sit in that manifold and come up with that. Even you can try the following, right? I think Shrikant did it last class maybe, or at least he has the code for it or something. You can just generate random pixels and wait till you get a first digit, right? Like a number 3 or something. You can just try, you can wait, and probably if you run it on your on the best supercomputer today, for the age of the universe, if you run, it might be difficult to get a single image. That makes sense. Okay, that's how difficult generation problem will be on a large enough image. All right, so that is where these algorithms have their power. So to come back to our geometry here, everything else is so vast that it is impossible to come up with a tight boundary. Okay, that's the first thing. Now, nevertheless, okay, let's just brute force ourselves, and like very often mathematicians do the following, right? Assume this is true and then come up with a contradiction, something like that. So we are engineers, we're not mathematicians. We'll assume it's true and see if we can solve the problem. If it's true, then we'll come back and see how to make that true. Okay, so I'll go to my second point here. Okay, so right now I have not shown you that a tight decision boundary exists, but I want a full end-to-end intuition kicking in us, and then we'll go and revisit number one. Okay, so we'll assume it's true for now. Okay, so what are we assuming? We are assuming that there is some sort of a so in this case, I'm assuming the existence of what is called an ideal classifier. Okay, and as I said, I'll slowly start using the word discriminator as we go more into the literature of GANs, right? We assume that there's an ideal classifier 0 or 1. So basically this guy for us exists. Okay, this guy here exists, where I have not given it the yellow, this orange points. I've given it only the blue points, and yet somehow he has managed to come up with a decision boundary like this. By the way, what does the decision boundary mean? This is nothing but a function. Remember, neural networks are functions, right? This is a function that is mapping your space R squared to a 0, 1 thingy. Okay, which means any point you give me, it will tell you whether it's 0 or 1, 0 or 1, 0 or 1, 0 or 1, like that. And that is how you construct the this kind of a decision boundary set. Okay, all right. So we assume that this exists. Okay, so such a function exists, such an ideal classifier exists. Now, if it exists, okay, now comes the nice geometry that GAN gives us. Okay, so this is where we use the same classifier. Okay, assuming ideal classifier, right? Assuming ideal classifier. Here's what we're going to do. Okay, so whenever I say an ideal classifier, that means that there is a decision boundary. Okay, there is some decision boundary. No, all right. Okay, this is where the generator part starts in. So I'm going to, so there is this z data. Okay, I'm going to assume, I'm going to come up with a function f from z to our space x, let's say. Okay, so this is some sort of a, I'm just writing both in the same graph right now. Okay, which is okay. And in the VA case, we needed all those latent space and stuff, but in this case, I'll just abuse notation and just write an x, something like that. Okay, what this has to do is that if you give me a specific value here, ideally it should come and give me a value here, x. Okay, so let's say z1 should go to x1, not ideally, ideally it should go inside this. Okay, but let's say it's not going for now. Okay, so the goal is this, right? The goal is to give me new images, new human face images. Human face images, I'm assuming, lie somewhere here. Okay, the goal for me right now is to come up with a function which will take my z and map it into here. But in the beginning, at least if your algorithm is just starting out without much knowledge, it might be mapping something like this. I take a random z2, my process is like that. I take a z value, z3, and then end up mapping it to x3. Okay, fine. Now, here's what I'm going to do. I'm going to say, update the function. Okay, update this function. So a function is nothing but moving a bunch of points x to somewhere else. That's what a function is in from one vector space to another, right? Except that try to make it go into this little structure here. That's my goal. So update this function. Aman, Z is not a latent space for us for now. Okay, for now, just imagine it's a function. Later we'll give more names for it. Okay, so update this function such that what? Such that all fz1, fz2 and all etc., lie inside the decision boundary. Okay. So here's a goal for us now. This is step 2, by the way, right? We are in step 2. Supposing it exists, update the function such that having mapped this, having taken this f, and from z, when you take z through f, you come to a place where it's close to the decision boundary. Okay, this is where a very nice innovation came in the GAN literature that said that, hey, if I keep the decision boundary fixed and yet I get a neural network to do the following, that is, learn in such a way that your function comes to be 1 here. So let's say the decision boundary does the following. It's going to print 1 here, okay, and 0 here. Okay, what does this mean? It means f of x. So I'm just going to call this shape S. Okay, so f of x equal to 1 if x belongs to that shape inside. So by S, I mean everything inside. Okay, this is what I mean by S. And f of x equal to 0 if x is outside that, right? That's all it is. So I'm just taking this whatever I'm representing graphically here into something like this. Okay, just to motivate some of the loss functions that pop up later. All right. Okay, so x should be high here, x should be higher, x should be low here. This is the classifier. So I'm using, so I should probably not write f here. So let me just write something like, I'll start writing d. Okay.
Maybe g of x or d of x, yeah.
Yeah, I'll start writing, yeah. I'll now start writing g and d. Okay. So just to be a little consistent with notation.
The other day I was reading some paper, and that's where basically they use f and g as the notation. F as the real function and g as the neural network function.
Yeah. No, we'll use G. Okay. All right. So we are now in a setup where we have these points and we want to learn a G function. So yeah, I'll just redo this. You have a bunch of points here. You have S here. Okay. You have G, which has to do the following. G has to take you from Z to X, which means it has to get you here. So this is X1, this is Z1. Okay. That mapping it has to do. All right. And this discriminator, so I can call this D only. This discriminator has to, if say 0, if X is outside, and D of X equal to 1 if X is inside. This is what it has to do. That's a discriminator or a classifier. All right. The generator has to do the following. Okay. Now we are going to construct a neural network to do the following, where we will see the classifier, just like our whatever was there in our TensorFlow playground. Okay. This, imagine some sort of a neural network happening, doing this, right? We've seen that neural networks do exactly this when the final output is a 0, 1, right? When the final output we use a sigmoid or something, when that is a 0, 1, we can view that as a decision boundary. Okay, that's a neural network. Okay, that's one neural network. We're going to do the same thing here, where G itself is another neural network that will take you from here to here. Okay, so now imagine the following structure. Okay, where the function G is now represented like this, with Z coming here and X coming here. Okay, that's the G function. And the function D has to give you a 0 or 1. Okay. All right. Put together, it almost looks like, if you look at the whole neural network now, it almost looks like, okay, Z is the input, output is like a sigmoid version or 0 or 1 or whatever, right? Classifier, right? However, what we are going to do now is we are going to keep this part of the neural network fixed. Okay. And this is where we have to be, this is where that extra bit from the usual neural network stuff, right? That little bit of extra stuff comes in here. The core innovation that Goodfellow brought in his paper comes here. Okay. What is going to happen if I keep this fixed? If I keep this fixed, then I can see that at this part, okay, at this part, I'm playing around in such a way that if I want this working, if I have this working, and if I want the generator here to put a point inside this, okay, this value should be high, right? The discriminator output should be high. So can someone tell me what should happen to the X? Remember, I want to fool the discriminator into saying that whatever I've generated is real, which means I want to push this inside here, right? So what is this part of the neural network is doing? This part of the neural network is training itself, meaning it is changing, updating the function. So this says update the G. That's what it means, okay? This is keeping it fixed. So can now someone tell me, what is it that the generator has to do to make the discriminator churn out 1 whenever it generates an image?
It should be trained so well that the X belongs to the D.
Yeah, right. So if you keep the discriminator fixed and train it in the following manner, that whenever you pass a Z, it goes through and the discriminator has to say it's a 1. So that means, as Suchita says it, in this step, so this is my step 1, okay? It's actually an alternative algorithm, but in this step, or actually in my, sorry, in this notation, it's step 2. So I'll just write 2 here, okay? I'm currently assuming ideal discriminator. So what this says is that put X inside the set, right? The set S or whatever, right? S or D or something, okay? There'll be an notational overlap, but you know what it means, okay? So put X inside the set of human faces, basically. Human faces, okay? Or real data, so to speak, okay? So meaning fool the discriminator to say that it is a real thing. That's one way of looking at it. The other way of looking at it is, can you move the value of X? So basically, this will update itself now to come into this here, right? X1. So this is good, this is bad. All right, this part is good, this part is bad, and that going from bad to good is training the discriminator. All right, okay, before doing the whole GAN thing, I'll leave a few Q&A open. Questions?
Ajay, is the dimension of this Z and the mapping to which we are going, is there any constraint on that?
These are all hyperparameters that you have to sit and tune, right? Like for example, if your X is, let's say, images of million pixels, then you'll have to start and sit and decide what dimensions you want. You'll try with 100 or 500 or something like that and see if it works, right? So these are all engineering challenges, but there is no real, from the pure the math point of it, there is no real restriction except the representing power of the
Got it.
neural network here, right?
Got it.
If you have a very small dimension here, you may need a more powerful neural network to be able to
Deeper and wider
push
network.
it to those kind of things, right? Yeah,
Yeah.
Yogi?
Earlier you talked about tight boundary, right? I mean,
Yeah.
if boundary is too tight, then it becomes very difficult. So in this case, the D, if there is a tight boundary, then D also can make a mistake, right? That it's little bit outside and still it is pushing inside.
That's true. So you don't want it to be too tight, because if it's too tight, then you'll have to actually mimic the training data. That's overfitting. That someone else also mentioned that.
Right.
We don't want that level of tightness, yet we want a reasonable amount of tightness over there.
Okay.
Okay. Yeah, Mridul?
Yeah, hi Ajay. Why didn't we design this solution as as you were saying in the start, right? We'll take a set of human images and we'll just take a set of non-human images and we'll try to make the neural network learn what is a neural image, human image, and what is. But that doesn't work, right?
Yeah, because the chance of getting a tight boundary means that you'll have to expose it to a lot of non-human faces. Now, how many non-human faces are there? Well, roughly something like this, right?
Right. Got
Of
it.
that order.
So,
So the thing is, it's impossible to come up with everything around it in that space, right? So the tightness will be very difficult to achieve. It's in fact it's intractable. It's impossible to achieve.
right, because the human faces are lying in a subspace of that huge space.
All the photos we have taken so far lie in a very small subspace of all the possible images, right? Even in a 1 megapixel resolution, you saw how big it is. Okay, like this. See, these are numbers where even Ambani won't know what it is, right? Up to a point, Ambani is good with long, he can handle like uh, crores of crores and stuff like that, right? But beyond that, even he has no idea what this is. Yeah.
Right. Got it.
Yeah, Mridul.
No, I was lowering my hand.
Okay. Anyone else? I want this geometry very clear in your minds before going forward. Yeah, Shashank?
Yeah, just one question. So I understand the way you are trying to say that we cannot, have all the non-human faces, but you are talking an ideal situation. But let's say you have been tasked to develop an algorithm to develop this classification boundary for a given data that is being provided to you. In that case, you can have a boundary. So
Yeah.
you can then,
If you have both, see, if you have two classes of data, you can come up with a decision boundary. But
yes,
just because data point is on one side of the decision boundary doesn't mean that anything in that space belongs to that category. Okay, let's take a simple cat dog example. Okay, let's say
sure.
I'm doing a simple, like one of the first deep learning assignments people will do. You have a few thousand cat images, you have a few thousand dog images. Okay, fine. You can use you can use SVM based stuff, you can use deep learning, whatever it is, right? Okay, and you'll get some sort of decision boundary like this. Okay, what this decision boundary is good for is that if you give cat or dog, it can distinguish. Okay, fine, it can. If it's good enough, you have given good enough representative data, and the new data that you give is similar to whatever you have. However, what lies here? Whatever lies here will be called cat. Whatever lies here will be called dog. So now, if your neural network, which takes in, let's say this is your neural network, okay, and towards the end you have like one now. Basically, towards the end you have 0 or 1, okay, and here you put an image of a cat, okay, it will say 0 if cat is 0, right? And if you put a dog, it will say 1. But what if you put something totally different? Well, the way the neural network is structured, it might end up choosing some. I mean, it might still say this is a cat when you give it like cat.
Basically, it's a
Whatever.
data drift problem for the model.
Yeah, in some sense, yes. Whatever you're testing it with is not
Yeah.
coming from the training distribution, which means it'll do nonsense on it. So it's not like, I mean, again, to say that it's not cat or dog, to say it's neither is also will also be a challenge now, because that not either has a lot of data coming out, right? So in
Okay.
this
Okay.
neural
Now I
network setup,
understand.
this is impossible,
Yeah, I understand now. Okay.
right?
Thank you. Thank you.
Ajita,
By the way, great cat picture.
thank you. Ajita.
So I was actually thinking about D, right, which is basically the target class of things that you want to generate. Is there any requirement on how big or small could it be? Like, I don't know. Can I ask it to generate more images which look exactly like my cat, which is going to be a very specific class?
You might need a few thousand. You might need a few thousand of images.
Okay.
Yeah.
But
If it's just your cat that you want to generate, maybe. Yeah.
good. And secondly, so you can also take it in the other direction. Right? I want to generate a cat or a dog or an elephant or a zebra or whatever, right? And then you have multiple classes in D. You know what I mean? I want to let me put it this. I want to generate an animal, which is a very, 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 very big data set.
Yeah,
So
That
these are
don't-
two extremes of this,
Yeah.
and both of these work, or is there a limitation?
Yeah, then that's where we start calling conditional GAN. You condition on what class you want to generate. Okay. So there are, right after these papers, people are doing all versions of conditional GAN and something called a cycle GAN, which is something I really appreciated. But then there is pixel GAN. There's this whole bunch of papers. So yeah, it's possible to get the algorithm to generate elephant, generate cat, generate dog, provided you have given all these three classes of images in the beginning. And there are ways to tune these internal parameters here to play around and generate that specific class. That is there. Okay, probably will not get into those things today. Okay, I mean, if you can grok the basic GAN architecture, then and read the Goodfellow original paper, then you will be able to read conditional GAN kind of things.
Yeah, I was just interested in if there is a mathematical limitation on it. It seems not. So then I'm fine. Everything else is engineering. Right?
Yeah, there's no mathematical limitation. It's all engineering. The math exists. The math shows that it's possible. The engineering efforts is what will come. This is like what I said with VAE, right? When I first read the paper, while I was amazed with the math, I just couldn't believe it until I went to GitHub, pull it, ran it on my laptop to see it generate. Until then, I didn't believe it's possible on a tiny data set like whatever, MNest or whatever. So sometimes the proof is in the pudding, they say, right? All right. Okay. Anyone else get this picture right? If this guy is fixed and this guy is training, meaning you are allowing it to change with iterations how it's throwing. The example I give is basketball, right? You're throwing. Imagine this is like a basketball hoop, and you're throwing it, and then there is this guy who says, "Hey, no, you're wrong." Then update yourself until you finally manage to get here, and you get a good reward for that, right? So that's one way of looking at this, right? You're updating your own ability to throw into the basket, and if someone helps you characterize this basket, you'll start doing it better and better, right? Someone says, hey, you undershot, but if you throw here, they'll say, hey, you overshot. Can you undo it? Maybe put lesser force next time, put more force next time if you're here, stuff like that, right? So then you'll start getting into the basket. Okay. All right. So is everyone convinced that if this guy is fixed and this guy is training, then the geometry that's going to happen is this fellow will go into the basket. This is the important geometry I want to communicate here. Because if this is communicated, then that algebra becomes intuitive. Yeah. Questions, or shall I assume everyone has followed that?
I just
one
followed
question,
one
Ajay.
question. With the what exactly Z will be? Some practical application. Z can be
Z is generally Gaussian noise.
okay.
You're starting from Gaussian noise and generating complicated stuff. That's the beauty of these algorithms, because anyone can generate Gaussian noise.
And then from there you can give a target that, okay, this is where I really want to be. Okay.
Okay. Yeah. Anyone else? The simple geometry. So this is atypical of a neural network that we are used to, right? Whoever has used neural networks, you will use it for a classification kind of a task. But here we are saying, hey, I'm breaking this full neural network seems to have two pieces where one piece is fixed. The moment a piece is fixed, the decision boundary is fixed, meaning the locations here, meaning these points where you have 0 and 1 are fixed. If this is fixed and yet you are allowing this to train, it simply means that you are asking these z's to fall into the place where discriminator is high. Okay, so as long as I'm updating g and keeping this guy fixed, so now I have to talk about the loss function. What is it that I'm actually minimizing or maximizing or whatever, right? Because whenever I say training and stuff like that, we need that. Okay, so as long as you've kept the discriminator fixed, think of what is the loss function that you want. Okay, you want the following, that is d of, see, this is d of x. Okay, d of x, but then x itself is g of z, right? So x itself is g of z, so d of g of z. Now should this be high or low? Should this be high or low?
Hi.
Right. So if this has to be high, then you are saying maximize this. But with respect to which parameter? With respect to G or D?
D.
Yeah? With respect to G or D?
D.
D, right? Okay. So this happens to be one kind of a loss function. It's not, I'm not there yet. I'm not in the place where Goodfellow was in the final equation that he brings in. But nevertheless, I get some intuition of what I want going on. Okay. Now, to be able to understand his equation, we need to do a little bit of changes. Okay. So, by the way, one more thing I want to mention here is that I want to maximize the expectation of this. Okay. An expectation you can think of by taking summation over the data that you have of Z. Okay. This is what I want to maximize. All right.
So Ajay, just one question, just repeating what you're saying. When you say max expectation D of G of Z, I mean, how do you say it in English? You're saying given Z, if G generates a value where the D is equal to 1. So we want to get max of D equal to 1, right? How do you, can you just repeat this equation? Maybe I'm not able to explain it correctly, but
Yeah. Update. Sorry. Hey, wait, my bad. Why did I write D here? D is fixed, right? My bad. I got lost in notation here.
right.
I'm
So I want to maximize G.
Yeah. It is maximizing with respect to G that I'm talking of. D is fixed, so my bad. Okay. It is maximizing with respect to G of this equation. Okay.
And moreover, D is 0 or 1 here, right? So
Right.
D will be 0 or 1, or if it's a sigmoid, it will be between 0 and 1. Okay.
I
Should
was about to
we
ask, the expectation would always, so how basically we would come up with the expectation, because D is either 0 or 1.
Yeah, it is summation over Zi, whatever, Zi to Zn, whatever, right? Or let me say I is equal to 1 to some capital N, 1 by N of D of G of Zi, where Zi is you take from random Gaussian here, standard norm.
also,
Okay.
since D is Bernoulli, it's simply that probability of D of G of Z is 1. That's all it is, the expectation.
Yes.
Ajay, one thing over here, shouldn't we like try to penalize it if that D ka output is 0?
That's what maximizing is, right?
I mean, in my head, we can just use that binary cross entropy loss here only, right?
Yeah, agreed. But I'm just saying, is this, you can do different loss functions, but is this fundamentally what you want? Do you get that this is fundamentally what you want? You can come up with variations of this. In fact, this is not exactly what Goodfellow does. He does a little bit of other things also. Okay, but do you get that this is what you want intuitively?
Right.
G such that for a fixed D, whenever you pass a Z through the generator, it ends up in a locations wherein the discriminator will give you a high value like 1.
Correct. Yeah.
This geometry, this neural network architecture, and this loss function or whatever, this objective, are you clear with?
So basically, if I take all Zs, I want to increase the probability that if I take 100 Zs, I want to increase the probability that like 90 of those 100 Z should like fall into D, or even maximize that, right?
Yeah. If your generator is good, if
Hmm.
it's getting the best possible, if it has if the perfect generator here is the one that will perfectly put all the points here.
All the 100 points, yeah.
Whether such a generator exists or not, how well it does, all that is engineering effort. But
Got
from
it.
see, you start with the best, you start with what you want in the objective function. Only then you get a loss function where you can do all your backprop and fancy stuff. That is when the engineering starts, right? So there is that initial part where the math has to set
Got
itself.
it.
Whether
Yeah.
it's possible for your data set, for your constraints, all that is engineering effort, right? That's where most of the man-hours today are in the industry. But how did Goodfellow initially? So we are now putting ourselves in Goodfellow's mind, right? Thinking of this. That's what we're trying to do. Okay.
Right. Yeah.
The reason we're doing it now is that it has worked. The engineering efforts are there for us to see that this person does not exist is the engineering effort behind it. All right. Okay. So if this objective is clear, I'll do a small tweak to this objective because to be consistent with the notation that he has. So if I'm maximizing this, then will you all agree that I can write minimize if I put a minus sign somewhere, right? I'll just redo this. I'll put a minimize now, expectation over z, and I can put a minus sign wherever I want, right? Minus d of g of z. Is everyone convinced with this part? No confusion, right? You're maximizing something is minimizing negative of that, okay? And adding 1 does nothing, okay? And then putting a log is also fine because log is monotonous. Okay. Questions? I'm just doing this to be consistent with the notation. As long as you realize that it's equivalent to saying minimize g of e of z of d of g of z. Okay. As long as you're convinced that these two are in principle the same. The best, maximize here. Maximize here and minimize there. Okay. Is everyone convinced with this? Any doubt in the algebra? Basic stuff, but just in case. Because it looks like unnecessarily piling up stuff, right? Okay. I'm going to assume no confusion. All right. Okay. So this happens to be one part of the loss function of GAN, which is the main focus of what we want to do today. Okay. Now the second part is the following. And in fact, I called this number 2. So we'll go back here. So if I said suppose 1 exists, right? Then we do the following. That is, we minimize over g of expectation of z of log of 1 minus d of g of z. Okay. Okay. So this is assuming such a d exists. So here, assuming this guy comes to us from here. Okay, that's what we are assuming. But we have still not shown how to handle the first part at all. We have just said assume it exists. We have solved this, but we now have to handle the second one. Okay, the second one is handled in the following manner, and this is probably the most beautiful thing you'll see. Okay, and the second one is going to handle this scenario where not faces are taken care of in a for those who come from a software background, you all know what a just-in-time compiler is, right? So that kind of that kind of a setup where the bare minimum part of the space you care about. Okay, so let me write this. Okay, so now remember we said we started with this. We said human versus not human. Okay, here let's say in the human, let's say you have some 100K samples. Good, you have sample data. Here, it is impossible to characterize. Impossible to characterize, right? Because of the vastness there. However, it's like the setup is like this. Can you only care about what the generator g of z is going to be. Okay, and this is where the game starts. Okay,
Can
so
you repeat this, Ajay, once?
yeah, I'll finish the argument. Okay, I'll not explain this. I've just putting the intuition of what I want here. Okay, so this not human part or this part of getting a type decision boundary is handled in the following manner. Suppose you have your good old real data. Okay, so this is real data. There is no boundary, nothing yet. You have a bunch of points that are real data. Now, you have a bunch of points you can sample from. Okay. Now, in this setup of my generation, okay, so by the way, this is my whole neural network. We are going to walk through the code also. Okay. This is my whole neural network. I said what we do if this is fixed. Now I'm going to say, suppose I let this guy run. Okay, then what's going to happen? This guy will give me in the beginning random, right? This guy will give me a few points like this. Okay, all right. All these are nothing but you have your Z1 here, you have your X1 here, so on, Z2, X2, whatever. Okay, some points. Okay, now, what if I call these as my class 0? And what if this is anyway my class 1, right? This is where the discriminator output has to be high anyway. So remember our goal. Our goal is to get a tight boundary like this. So we are going to the output 1 if it's here, output 0 if it's here in some sense. So something as dumb as a decision boundary like this. Suppose, imagine a simple logistic regression kind of thing in your brain. Suppose I have this in the first iteration. Okay. So now this becomes my D of iteration 1. D is a decision. D, when I write D, I mean both the discriminator as well as the function. Okay. Discriminator. All right. Decision boundary and discriminator. For me, they're identical, right? One perfectly characterizes the other because it's a function from either 0 or 1. All right. Now tell me, what should now go back here? Okay. Imagine that this is your decision boundary. What should your generator do? See, I've done one step now. I've asked the generator to generate something, called that my class 0. I have class 1. I have this decision boundary, standard neural network stuff. Now, on this decision boundary, if I now again do this game of G and D, what will the G do? Remember the objective of G. The objective of G is to sneak into whatever decision boundary currently exists. Right? Do you agree? The goal of G, so notice this, right? Goal of G is to sneak into the decision boundary. Okay. So what am I doing? What will the second, now with this D, what will happen to my G?
It will try to go on the other side, right?
It will cross the boundary.
Right.
Yeah.
Right.
Awesome, right? So now in the next iteration, I'm going to jump here. I'm going to jump here. I'm going to jump here, right? I'm going to jump here and so on. So this will be my X1, X2, X3 and all. Now, having done this, call these fake data. Now call this class 0 for the new setup. Ignore these guys if you don't care, right? Call this class 0. Call this class 1. Now what's going to happen? Now update the discriminator. What will the discriminator do?
Further shift right? New line.
Further shift right. So the new decision boundary comes. Okay. So in my notation,
Ajay, you said D is fixed, right?
D is not fixed now. D was fixed. D was fixed alternatively. D was fixed D was fixed when I peeped into the boundary. D was fixed. Then I update D. Now again I keep D fixed, update G. So now what's going to happen? Now this is going to go further inside here. Like that. Then a new decision boundary will come. Notice that these are not perfect. These are not really. So now I'll repeat my argument. Okay. Not human is impossible to characterize. But what the G of Z is going to be is what I'm going to characterize as my fake data, as my class 0. This will be my class 1. This will be my class 0. So I am iteratively updating the decision boundary, then keeping the decision boundary fixed, updating the generator, then keeping the generator fixed, updating the decision boundary, keeping the decision boundary fixed, updating the generator. So updating generator is putting this guy in here. Updating generator is putting this guy in, peeping him inside the decision boundary. Then keeping these guys constant, draw a new boundary. Now, it is true that this, whatever comes out here is not tight, meaning it's not going to do well here because these are non-faces, yet it's going to say it's a face. The way I've drawn it, right? The way I've drawn this decision boundary, it means everything on the right is a face. This non-face thing is a face, but I don't care about it. My tightness of boundary should only be in the place where the enemy is going to attack. right? So you have a vast empire where you have infinite boundaries essentially. Okay, not infinite, but intractable number of boundaries. But you know which side, as long as you know which direction your enemy is going to attack, you put a fence there, right? Enemy is good enough, he'll come in like that, like that. Yeah, Mridul?
So in every iteration, you are telling the discriminator that whatever G has generated is
Call it
bad,
fake.
and
And then draw a line. That line will keep getting tighter only in the direction from which the generator is attacking, which is essentially all I needed. Because my goal is to make the generator come closer and closer to my main guys.
right. But what if your generator does so well, and then I mean
Good,
your
right?
generator starts making faces, and but then you still tell that oh you are fake. Then
Then no, no, no. There comes a point where discriminator cannot really identify, and then you throw the discriminator away, and then you take the generator and you create a website like this person does not exist.
okay.
That's the goal, right?
That's
We
the
have
goal,
reached
right?
our
Don't lose track of our goal. Our goal is actually throw this into the tight decision boundary.
Right, yeah.
There should come a point where the discriminator does not do well. Yeah, Aman?
Just one more time, what basically we tried to do, we took some green points, or rather, we actually started from Z, that Z1 where you have put in the cluster, where we actually generated a decision boundary D, and rather that's where basically we started getting the points x1, x2, x3. Then we kept x1, x2, x3 constant and
Yeah.
drew our green decision boundary.
Yeah.
The next time what happened, like where the pink one came in, is what I wanted to understand. How did we come to the pink or the purple whatsoever? Yeah.
What is the generator trying to do? Notice, if there is a decision boundary, the generator will put it inside the decision boundary, right? That's what we
Yes.
just argued out.
Yes.
This whole loss function, we argued out that the goal, if decision boundary or discriminator is fixed, we argued that this guy will go into here. That was our deal in the beginning.
Correct.
With that deal, if this is my decision boundary, then generator will peep in the next iteration, it will peep into the decision boundary.
So are these x1, x2, x3s are getting updated for the decision
the
boundary?
generator gets updated. Yeah, the generator gets updated. So if you go back to this picture now, you have your you have your Z, you have your generator, you have your discriminator, you have this X that comes out, and you have 0,1 that comes out, right? So if you go back to this neural network here, at one point I'm keeping this fixed, which means I'm keeping the line fixed. Then update this guy goes inside the line, wherever the line is, right? Wherever the line is, it's going to cross over.
And for drawing the next line, you are actually using the previously generated x1, x2s. Okay.
Yeah, that makes the line tighter.
Line tighter. Got it.
But only in the direction where the disk generator is attacking it from. You are in what space? You are in 10 whatever that.
Yeah.
Right? You are in a million kind of dimension space or something. Okay. If you're a megapixel, you are in essentially a 3 million dimension space. So you can be attacked from any direction.
Yeah.
But for the specific generator that you are starting to train, you only care about putting a fence in that part. You don't care about putting fences elsewhere. However, if the generator ends, if eventually the generator starts putting data here, you will draw the fence like this now. This time the fence will come there. So the fence keeps on updating so that you don't attack it. But then you keep on updating the attacker to go in. The defender updates, the attacker updates. The defender updates. Eventually you come and jump into the hard, meaty portion of this, which, remember, was our ultimate goal.
Correct. So one more following question here. If I look at it as a very layman example, it would be some prompt where I would ask, hey, give me a photo of a person with so and so characteristics, and it will try to give me a generation of a photo in a way. So all my input was a prompt. I don't have any direction as such. how the neural network is basically internally going and updating itself. From one prompt, it is generating one photo at the end of the day.
Yeah.
So how
Yeah.
do you decide that from where you need to put the boundary?
Yeah, in that case, you're not see, once a generator is trained, you're no more going to update decision boundaries and stuff. You're just going to start with the Z and come up with an X. The goal here is to choose X in a proper way.
Okay.
Sorry, to choose Z in a proper way, because now different parts of Z will map to different parts of X. And this is what we saw in the VA. Remember that animation I showed?
Yes.
There were 3 colors on that Z space there, and they all
Yes.
went. So your prompt is nothing but choosing one of those regions in Z and then
Correct.
going.
Got it.
That's
Yeah.
one simple. So your effect of your prompt comes here. Okay.
Got it. Yeah. I think aligned. Thanks, Ajay.
Ajay, I think part of the problem is that we motivated the loss function, but we didn't optimize for moving the discriminator. Discriminator thing was not a part yet, right?
Yeah.
That's what I think is
the geometry of the discriminator. Yes. Okay. So yeah, coming back to our story here. If my if my generator is fixed, okay. So now I'm in the classical machine learning setup, okay. If G is fixed, then I want to optimize over my D. So what should happen to D? Tell me. What should happen to D? So notice this, right? This line that I'm drawing, if I use a green color here, right? What is this line trying to do? This line is trying to say D of X is equal to 1 if X belongs to my data, or if X is drawn from P data. Okay, now I want someone to finish the argument for my. Remember, this is now a binary classification problem, right? The binary classification problem, I have told you what happens to class 1, that is these points, in the green color setup. In the green color setup, I don't have these blue and magenta lines. I just have this guy and this guy. Okay. I have 2 sets of points. I'm drawing this line. How do I draw this line? My loss function, my discriminator should be X equal to D of X equal to 1. If X comes from P data, which is what this is, right? What should happen? What is the other thing that has happened?
Should be 0
If
X comes from Z.
yes. Yes. X
G.
comes from Z is as good as saying, so then I might as well write D of G of Z equal to 0, where Z comes from your PZ, right?
Yeah.
Is that what we're doing? The discriminator, if it has done its job, has done the following. So now coming to the loss function here, right? From a D point of view, I want to, from a discriminator point of view, I want to minimize over my D G of Z. Sorry, D of G of Z. Okay. This is just on the generated point, but from a generator point of view, I want to maximize the D of G of Z. 2 things are happening alternatively, right? You have to minimize D of G of Z over D. You want to maximize D of G of Z over G. Okay, that's the thing we are going for, right? So I'll rewrite that here. You have to, from a G point of view, you want to maximize over G, D of G of Z. Okay, but the same thing you want to minimize here. Okay, is everyone following?
Yeah, the expectation, right?
Not really. I don't follow.
We're trying to
Maximize over G, dg of Z, but I didn't understand the minimize part.
This is the minimized part here. D of G of Z should be low, right? You get, that's exact. This is a basic binary classifier here, right?
Aman, if it is a fake, I mean, the discriminator wants to catch the fake data, basically. That's all.
Yeah.
So it should say, okay, Aman, did you follow this?
Yes.
Okay, if you followed this, then tell me, should this be low or high?
This should be low.
Then what is this saying? Is it
Okay. I think, yeah. And
right?
P of Z is basically our Z space that the small.
Yeah. Of course, I mean, I have to put some bells and whistles and all that. I'll do that. Okay.
Yeah, got it.
Yeah,
Yeah.
you have to. So Z is always, Z is something we already know, right? Z coming from.
Yeah, got it. Yeah,
That's
I
always the
think
case.
we missed that.
Yeah.
Minimizing just means we want to minimize the fakes. We want to
You-
have as little fake as possible.
No. Number of fakes are kept, right? You want to make sure the line is such that it has escaped. It has not, the line doesn't come like this. If the line
Okay.
comes like this, then on these values it's saying 1.
Yeah, okay, fine, thanks.
But minimizing means put it here.
Basically, we are minimizing any escape from the deviation. Basically.
Yeah. Any of these lines for that green versus yellow, any of these lines are good discriminators. But if I'm coming like this, then on x4, this value is high. It's not 0. x4 means z4. Z4, g of z4 is x4, right? Notation.
I mean, I'm trying to like make all the G of Z as fake as possible until I cannot, right?
Yeah, d of g, d on all the generated ones, you're going to make 0. That's what I mean when I draw a decision.
Yeah, I mean, out of that generator, whatever comes, I will keep on, I'll try my best to say all of them are fake until I cannot.
Yeah, exactly. That is what this line is saying. The geometry is here, the neural network is here, the algebra is here. I'm still not done. The full glory of the loss function is yet to come out, right?
Because the discriminator also needs to see the true data and has to be trained on that too, right? That's the point. Only then it can discriminate. So that's why that part of the loss function is still not
missing. Yeah. This alone won't work, right? This alone won't work. So then, what should happen to D on X? On X, my D should maximize expectation of X followed as P data of D of X, right? That's just me writing this sentence in the as an optimization loss objective. Okay. Questions? Simple, right? This, see, as long as you understand I'm doing binary, this is just binary classification for now. Think of your first class on logistic regression. You have a bunch of points here, you have a bunch of points here. Ignore all the other colors, only focus on the green and yellow ones. You want to draw a line. That means the decision boundary should be 0 here, it should be 1 here, the function D, right? That's what we have written here, right? Just that another way of writing this in a way that can be used as a loss function with all that backprop fancy stuff is this, right? As long as the equality between this and this is clear, we are now walking towards a differentiable loss function which can update the discriminator, right? So here is all the discriminator stuff, the decision boundary stuff. Here is the generator stuff, right? I have to merge them properly now, and that is when the loss function truly appears. I'll still wait for a couple of questions before building out the full loss function, because now after this it's very trivial. It's just simple algebra after this.
I have one question. So in the whole process of this discriminator weighting and this other thing, like minimizing that thing, and so we have assumed that the discriminator is fixed, and when the discriminator like tuning is happening, the generator is fixed, right? So does, like, now once you bring this all together and compute the total loss, will that that one thing remaining fixed when the other is getting optimized and the other thing vice versa, does that also needs to get captured when you're defining the loss, or if you just
Yeah.
okay, then I'll wait for that full thing to
Yes.
happen.
Yeah, the loss function will capture it. Okay, loss function will capture it, and in the code you'll see it very quickly.
Okay.
The code will give you the algorithm that Goodfellow writes, and the code that we show should give you all the intuition you need. Okay. Any other questions? Arsha, Abhishek, Shantala, Preeti. Is everyone convinced with this, or is there some doubt? I don't know. Like when there is no doubt.
Convinced.
Huh?
Convinced.
Okay. Give me okay, yeah. Suchita has given thumbs up. Give me thumbs up if you're convinced with what's going on. If that whole picture is in your mind. I only see Shashank and Suchita.
Okay, no more.
Okay, most of you are giving thumbs up.
Ajay, I just have one question. Here in the right side, you have written d of x is equal to 1 and d of g of z is equal to 0, right? So does that mean for so d of x, even if it is greater than 0, then does that mean that it would have crossed the line? Or we are making that calculation as closer to 0, or is it going to be always 1 and 0? Yeah.
If it's a sigmoid, then you'll have a threshold and so on, right?
Okay.
It's think back to your logistic regression days, right? Your final output was like a probability, and then you put a threshold and you call class 1, class 0, something like that, right? But this is what we want ideally. Therefore, we try to achieve this via an objective.
Okay. So there
Right.
could always be a possibility where a fake can still cross over the line.
Yeah. If the number of samples you have, number of epochs you run, and the power, if you use a very dumb like if you use a very like a linear style decision boundary logistic regression style, and if these x's are all over the place, then it will obviously not work. You need a powerful enough discriminator to come up with fairly complicated decision boundaries.
So even there are a set of discriminator functions that we have to use in this case, like
Yeah. Discriminate.
these are all standard.
Typically it's a neural network, right? So you may use
Okay.
based on your use case, you may start using multiple layers and stuff like that.
Okay. Yeah. Thank you.
Preeti?
Yeah. So Ajay, here we are able to get very close to class 1 by shifting the discriminator towards right, and we are able to then basically reach a state where discriminator is not able to distinguish between what has been generated via Z and what is the actual real data, right? Is this possible? Why? Because we have limited set of real data, or like for
No,
example, yeah.
no. If your generator is doing a very good job, then and if your discriminator, see, you cannot use an infinitely powerful discriminator. You
Right.
cannot put. You have to have finite number of neurons and stuff like that.
Right.
Okay, but beyond a point, so for that fixed level of complexity, that is via some sort of hyperparameters, right? For a fixed level of complexity, as long as this guy is also good with representation, he will be able to fool the discriminator enough, right? So that it can never really draw. Imagine if all these points come very, very, very close to this. And the discriminator cannot really, draw very, very complicated shape of line to weed out the generated points. That's when it fits, right?
So, for example, suppose if you wanted to generate a non-human image, then it means that we won't be able to generate a non-human image following the same algorithm.
No. The way you're trained it is to make it come and fall here.
Assuming that class 1 is a non-human data.
No. Class 1 is something we want to mimic.
No,
it could be a bunch of, it could be, as Suchita said, right? Dogs, elephants, cats, like that. It could be that class 1 could have multiple images, but they're all currently being called class 1. Okay. So it'll gravitate towards some or the other of these. We have seen that in the VAE one, right? Where that whole Z space got pushed into 3 places. Right?
So the class can have any kind of like image.
Yeah. You could have multiple types of images to generate. And as Aman was saying, there is a way of controlling which one to do, which one to generate in the beginning here. Right? So even this has a lot of engineering efforts, how to choose this and go there. Okay, all right. So if this much is clear, then we are now at this point, I can actually move over and show the loss function that Goodfellow wrote, but let me just write a couple of more lines, then it becomes smoother. Okay. So I'd mentioned that instead of this, so let me remove this part here. I need some scribbling space. So instead of this, he actually writes max over G of expectation coming via Z as that thing itself. And sorry, not max. He writes min over G with a minus sign. I just wrote that previously. With the minus sign, I can write a min. But then he prefers to write it as 1 minus and then puts a log on top of this. That's fine. Okay. That is one thing. And here also, if you look at, so notice that these two, the function is the same, except one is max over G, one other is min over D. So suppose I do the same thing here, min over D of E of Z coming as P of Z of log of 1 minus D of G of Z. Okay, so let's do that. Okay. Notice that these two are the same expression, except the min over G is and max over min over G and sorry. Yeah, min over G, min over D. No, sorry, what did I mistake something? Now it becomes max here because of the minus. Now it becomes max. Okay, and this anyway, so this got replaced by this. Okay, so now let's focus on these three equations here. This part is 1, this part is 2, and this part is 3. Okay, so if I think of merging both of them, I know that I'll merge all these three equations here. Min over G I can write, max over D I can write. Okay, I'm merging them. Remember that this expression is common for both. There's a min over G, max over D. Okay, and this function is nothing but expectation. So I'll write the first guy, x, that is this guy, equation 3 I'm writing, x coming from P data of D log, sorry, he puts a log there, log of D of x. So I might as well put a log here because its maximization doesn't get affected by monotonicity, maintains that. Then there is a plus, then there is expectation via Z coming as P of Z of this weird looking thing here, log of 1 minus D of G of Z. Okay, this is the full glory of the equation that he brings here. Okay, fine. Is the thing in red clear? There are three equations that are merged together.
Not
There
clear
is
to me.
Huh?
If you could, not clear to me if you could repeat. I could follow till 1, 2, 3, but how did you consolidate everything in the last red?
Okay.
If you could repeat.
Equation 1 is here.
Okay, min of G. Okay. Okay.
Okay. Equation 2 is here.
Okay.
Equation 3 is here. Okay. And this equation, Karthik had raised your hand. Karthik, you had raised your hand.
For
right?
me, the first equation was not clear. We are trying to minimize z like the values that produces from the, z, right?
Okay. Imagine
Yeah.
You're talking about this, right? Okay.
Yeah.
In this setup, what you are trying to do is you are going to imagine that you have the decision boundary. Okay. Now, what is your goal? Your goal is to move these X guys closer to the ideal set, that is the data distribution, right? You're going to bring that here. That is your goal. Now, if this discriminator boundary is fixed, okay, which means this part of the neural network is fixed. And if you are allowing this to be trainable and you can update and so on, okay, you are basically taking this set of Z thingies here into that part of the space wherein the discriminator is going to call it 1, which
Hmm.
means these guys are forced to go inside, peep into the decision boundary. Why? Because for this green line, everything on this side is called 1, everything on this side is called 0 for the green line.
Yeah.
That's what the decision boundary is, right? This
Yeah.
is what I mean, this actually I motivated it here itself, right? This is where I
Yeah.
motivated loss function. I don't know if you missed this part of the lecture, right? So you have a decision boundary, which I'm going to write D, which is also nothing but the discriminator function itself, 0 or 1. And you're going to, this is becomes a good point for a generator. So this guy is fixed. This guy is fixed, which means the decision boundary is fixed. You're training this end-to-end neural network with this guy fixed. And the only way to motivate this guy to go here is to make this guy call 1 on the point that this thing has generated. But because this decision boundary is fixed, the geometry is going to do the following. It's going to fudge it into the point where the discriminator has to say is saying 1. That is the only way. That is the only way you'll get it there, right? So the
Yeah.
geometry says keeping this fixed is moving Z into the circle here. The algebra says maximize. Algebra says give me a value. So the requirement, right? The requirement is the following. So when I say put X inside this, right? This require, if I write it as a requirement, then D of G of Z should be 1. That is the requirement. And because D is a function 0 or 1 kind of, or 0 to 1 kind of function, this statement can be achieved if you maximize this.
Yeah.
That's it, right? The
Yeah.
discriminator and the geometry, the equation, the algebra and the geometry have to go hand in hand with this for us, right? Yeah, Suchita?
Sorry, this is a painful question. Shouldn't there be a bracket in the equation that you wrote, or am I reading it wrong?
Which one? Which equation?
The red one earlier.
The combined loss equation that you wrote that has a min max exactly. So the whole expression there is in the brackets? Okay,
Yeah.
fine, thanks. Sorry, that's my math brain. Okay, thanks.
Yeah, you're right. Yeah, because these variables are here. Notice D and G variables are here. So I mean that.
Yeah, thanks.
Oh, the Discord comes from my system, is it?
I
Let
think
me-
so.
I think so, yeah, because all of us are muted.
Yeah, it has
Yeah,
to-
it's like tung tung tung.
yeah. Let me just kill Discord for now.
I have been so tempted to send you messages on Discord just to verify my hypothesis that it's your Discord pinging. I did not.
Okay. All right. Yeah. Any other doubts? So yeah, we are at a point where we can now move over to the original paper and look at this and say, hey, I know what this is doing, right? While this looks like a complicated equation, if you break it down in the geometry and if you know what a simple classifier is supposed to do, okay, then what happens when you freeze this, right? Then you get this. Now coming back to our two-step thing here, type decision. So this part got achieved by our maximize over D, some expectation of X or D of X, and then expectation over Z of 1 minus log something, right? Okay, something like that.
Log of 1 minus.
Oh, sorry, log of 1 minus. Yeah, log of 1 minus. You see why math needs 2 instructors? Yeah. All right, something like that. Okay, so this is, so while this is not a tight decision boundary, it is only drawing the decision boundary where the generator is attacking it from, which is all I need, frankly, because I don't care about the rest of the million directions in which I can get attacked, right? My enemy is attacking me only from one direction, so my decision boundary is being tight only there. So this becomes tighter and tighter and tighter, and that's how the discriminator updates. Generator, it's like a basket. So now the analogy of basketball comes in the following manner. There is an actual basketball player throwing. The ring is invisible. There is a referee. And now someone else comes who's not a basketball player, and who starts throwing in. So these are the actual basketball player shots. This guy is throwing stuff. All you have to say is, hey, this doesn't look like what that guy threw. I don't know where the ring is because ring looks invisible. So we are kind of estimating both the ring as well as updating our basketball skill to go into the generated ring, right? Fake, whatever, the updating ring. So the ring is also updated. Our shots are also updated up to a point wherein whether it was actual basketball player who threw it or whether we threw it, we don't see a difference. Okay. To come back to the basketball analogy from early. So earlier I took basketball analogy where we had a tight decision boundary, meaning the ring was there and all you have to do was put inside it. Okay. But now you're estimating the ring also. And that is where GAN became beautiful, right? If ring exists, then it's a standard neural network. Estimating the ring is where the challenge came in. Yeah. Iraban?
Yeah, so question is like if what we are trying to generate is an image or maybe let's say some sample data points like which are like single instances, then this is fine. But I was thinking in terms of sequences, right? If we are trying to generate a sequence, how will that look like?
Can you characterize the sequence as from some sort of a distribution, right?
Sequences, I mean, you have like, let's say like you have 10 time steps for like one sample is 10 time steps and you have 100 samples, right? So basically, if I now try to think of that 10 time step wala sample as like one X yellow point, right?
Yeah.
Then how does this thing work? Because like I'm trying to think in that way, like
First of all, you can characterize that part as a high dimensional vector. Now your only thing is condition. It's like a moving window condition on it, right? You are still in the conditional GAN kind of a setup almost, where you're conditioning the next part, next vector, next window is conditioned on the previous window and generate something like that. So it's not impossible to bring it in the same model that you have here, except that you'll need aspects of conditional GAN in there. And that's something we may not go into in today's class. I mean, we'll not look into the different variants of GAN out there. Just that once you understand the original paper, any version of GAN, the mathematical innovation you'll be able to capture. Okay.
Oh.
And conditional GAN is one of them.
Hmm.
Okay. All right. So with all this, right, let us walk through a small bit of code. Shrikant, do you want to add something here? You want?
No. I mean, the people wanted to see the derivation. If they stay back, I can do a bit of calculation. For one want to see why it converges or something.
Okay. Yeah. If you find this math to be basic, we have Shrikant sending you into a different world later. Okay.
We need something to disturb our mind,
Yeah. If we have not in, yeah. Oh, by the way, so this loss function now lends itself to an algorithm, which is ultimately what we want, and a small bit of code that will generate.
By the way, before I go ahead, I want you to appreciate Ajay's entire exposition, because Ajay, can you go up? Can you go up in this paper?
Okay.
I want you guys to appreciate that this is the introduction, related work. And in the next, okay, it starts here, introduction, come down. And then whatever, related work, literature survey, come down. And adversarial net, okay, one paragraph and they wrote that. That's what Ajay spent all the time on, actually. Ajay essentially explained to you what this paper and this, people are asking, right, reading papers is hard. He essentially, like, people who are like used to math, when they read it, they instantly understand it, like in one pass. But really, the paper doesn't really explain, right? After that, it's all proving. After this is all math proving that the algorithm converges and so on.
Yeah. Actually, we so far read like a couple of pages of this paper.
Yeah.
Okay. Yeah.
Right. So we can go to the code, I guess.
Yeah. No. We can look at this part, the algorithm part of it, right? So notice what he says. Okay. Mini batch, stochastic, blah blah blah. Again, number of steps to apply to the discriminator is hyperparameter. Okay. Meaning, do you alternate or do you keep the discriminator fixed? Update generator multiple times and then update. A lot of those are engineering stuff. Okay. So let's read this. So you sample a bunch of these Zs, okay, and sample a bunch of actual data. Okay. So what he's saying is, okay, let's start the story here. You sample a bunch of Z, which essentially gives you g of z, which I've written as these xi's here, and then a bunch of the actual data that you have. Okay, so that's what he's done here. Update the discriminator by ascending its stochastic gradient. Notice that from the loss function, he's only looking at the d part of it. So in my explanation here, I'm saying, oh, draw this line. That's what I did. So I said, draw this line is the first step. So first, randomly generate these samples via the first part of the neural network, come here. These are nothing but these points here. Okay. Then update the having kept that part fixed, draw a line. That's what it means here. Okay. This means draw a line, or whatever complicated decision boundary it can. Okay. For us, it's just, okay. Then, yeah, do this and then come back here. Now, sample n noises and update the generator by descending its stochastic gradient. So now it's the d loss function. The other part of it is not needed because that was purely on g. Okay. So notice the loss function here. So now it's saying, hey, having come up with this line here, keep the discriminator fixed. Okay. And update only the generator loss, which means keeping this guy fixed and only updating this. The way it will achieve the objective is by putting these new magenta style lines inside the decision boundary here, right? So that is happening in this part here, right? Make the points cross the boundary, right? The fence is broken. You're moving into the boundary. Now again go back here, update the boundary, draw a new line, and so on. So this is how the algorithm comes in. Okay. All right. So if we go through we can look at the code to generate this. So we have a generator, we have a discriminator, and we have the final GAN architecture in this. Okay. And I haven't run this code. Okay, seems to be running so far. All right. Okay. So let's analyze step by step. We have a data set. In our case, both data sets are two-dimensional, the Z data and the X data. In the very example here, you can actually modify this if you want for larger ones. Okay, wait, I'll just show the results first. This is very beautiful. Okay. Notice figure 1 is here, figure 2 is here, so on. Notice what's going on. Okay. The thing that's happening here is that I'll explain what this plot is doing. Okay. This plot has two things here. Okay. So on one side, we have the generator samples. Okay. And on the other side, what it's drawing for us is a specific shape of real data. Okay.
Basically the distribution, right?
Huh?
Basically the distribution of the real data.
Yeah, the distribution of real data is what this is. And the function has to map and put this here. Okay, that's what it's showing. Okay. So here, Z is my latent space, Gaussian 0, 1. In this case, after enough iterations, the generated and real are almost along the line. Now, in between, so basically, if you go back to this picture here, right? In the beginning, generated and real look very different, right? So if I look at the, let's say, figure 1, okay? In the figure 1, we are all over the place. Like the real ones are always on that parabola kind of shape, and the generated ones are completely here somewhere, if you see where my arrow is, okay? And if I go to the next figure, after a little bit of iterations, it's still figuring out. It's not yet there. Okay, it's still figuring out and going ahead and so on. But by the time we are into figure 5, we are almost there. Okay, so this is also the shape. Apart from the points here, the contours that you see are actually the discriminator contours. Okay, this is similar to the TensorFlow playground I was showing earlier, right? So we have played around with this kind of a thing earlier. So we are doing that in the code here, and that's what we see. Okay. Hey, where did that go? All right. So as iterations increase, we are coming closer and closer to the true distribution. Okay. So this is the code I want you to go back and play with. All right. And I'll explain the most important parts of it. And it's essentially doing this. If you understood this and the algorithm, the code should be very trivial to follow. Okay. So let's do step by step. We are starting the generator from a two-dimensional back to a two-dimensional. In between, we are going slightly higher. Okay. So what this means is that I'm taking 2 neurons as input and giving 2 neurons as output. But in between, I have some multiple layers, 64, 64, whatever it is. Okay. You can play around with those numbers if you want. But final output of the generator is 2 volt. That's what I have here. Then there's a discriminator. Discriminator has to take this 2, but that is nothing but this guy here. Right. It has to give you these 2 values. It has to input these 2 values and then give me a sigmoid, right, for a 0 to 1. Okay. And with a single value there. So this is like a standard binary classification setup. Okay. That's where we got all the decision boundaries, right? So these 2 neural networks are very, very simple. Nothing fancy about it. Net of Z is what you run. Net of X is what you run. And they're literally that. Okay. So I can close this out. Okay. Now comes the tricky part where you have to train the whole architecture. So in the GAN class, we compose these 2 guys, self.g, self.d. Okay, we choose those famous optimizers and so on. We use a cross entropy loss because we are still in the setup of classification, right? And so real data comes to us from a specific sampling technique, cosine sine. That is that you can again play around with different versions. You can try a Gaussian mixture. In fact, it'll be nice to try how from a single Gaussian it goes to a Gaussian mixture, right? You can try out those things if you want. Sorry, this is t comma t square. Okay, so I tried a circle also earlier, I think. Whatever, t comma t square. That's the data that you get. Z is your Gaussian and fake is your self.g of z. Okay, so in my picture here, this is what I'm going to call fake. Okay, this is what I'm going to call real data. Okay, that's the picture we want to keep in mind. And discriminator on real is one thing and discriminator on fake is another. So these are the 2 discriminator outputs. Remember, self.d is the discriminator. And the criteria I'm going to do is the binary cross entropy, right? So on real, you have on real and on fake, all right, mapping them. And that's it. I mean, so in the first part, yeah, Aman, question?
Ajay, I didn't understand the D real and the D fake on line number 56 and 57. Why we had to go through this? I mean, like based on our explanation, we were not going to for the discriminator for the real. I mean, like we were just going for the decision boundary, but here looks like we are trying to discriminate both the stuff.
Yeah, we need both, right, for discriminator. How the whole story is that discriminator can only work in a supervised setup.
Got it. My bad.
Yeah, be able to draw a line, it needs to know both the positive and negative classes, right?
Yeah. Looking at this equation, I'm able to connect.
Yeah, it is this equation. It's basically this equation here, right?
Yeah.
So this D loss is nothing but this equation, okay? And the G loss is nothing but this equation. So this is D loss and this is G loss.
It's an interesting thing to note that the generator part of it never sees the data.
Yeah. In fact, Shrikant was mentioning, if you can almost think of sending data without really telling you what the data looks like, right? As long as imagine I have an API that gives you a discriminator, okay, and you just generate samples. You're not really passing any information. You're just saying real or false. Okay, so there's no data that comes here. Just a discriminator that says yes or no. And from here, from the other side of the server, you can actually generate data. So without passing the actual data, you can, in some sense, pass some versions of the data, not the actual data, but something that mimics the true data. Okay.
It's like, let's say you want to generate photos of your family members, but obviously you don't want to give it away to some website, right? So in this case, it will sort of produce something that looks like that. I mean, of course, it won't be true.
It cannot be only that, right? I mean, just a yes or no. It has to sort of, it has to guide in which direction it will have
No,
more success.
no. Notice this. Notice this guy. Notice what we are saying here, right? Look at this guy. What is he saying? Hey, if you give me part of the space, right? If you give me any part of the space, I'm going to give you just a 0 or 1 or a 0 to 1. That's all he's doing. That's all he's doing. That's what the line
No,
is.
no, yeah, sure. So I think, okay, sorry. I was talking about the example of something like
Yeah.
family photo generation or something like that, right?
Yeah.
Because it's not just 0 or 1. It's not like, because every family member looks different, the characteristics are different. So you sort of have to have something more there than just 0 or 1. Here in this example, it works.
No, the point is, okay, let's say I'm the discriminator. Okay, you start generating, and I simply give you a decision boundary. You update your generator until you come closer and closer to my stuff, right? That is what is going on, right? Until you come closer and closer to my stuff. Now my stuff could be a bunch of images or whatever, animal images, family images, whatever it is, right? You'll keep on coming closer and closer to it without really seeing the data at all. That closeness to the data is characterized by the decision boundary, which distinguishes what you are generating and what I want to be generated, and you keep on coming closer and closer to the boundary.
But
Okay.
I mean, like, but it,
Yeah.
sorry, Sujit, please go ahead. Yeah.
No, I was just saying, I think I understand. Please go on.
But Ajay, I think I have a follow-up question. To discriminate, like even for our scenario, if you go to that equation, it have to see the real data, right? The d of x that in the equation that we were seeing, the first part, the
The
log of d of x.
generator doesn't see anything of x.
Now I'm talking about. Oh, okay.
Discriminator sees, generator doesn't see.
The information of what x is simply a binary for him via this guy, which is nothing but this line here. All it knows is it has to go through the line. It never sees, the generator
So
never
it's actually dependent on discriminator to tell generator whether it is a. Okay, got it.
that is what it's doing here. The whole GAN stuff is characterized, if you understand what I did when I said draw line, peep into it, draw new line, peep into it, draw line, new line, peep into it, and so on. That
I think
whole
this
thing,
closely goes with that example that you gave for that blind basketball guy.
Right,
Because
exactly.
that guy is blind, he doesn't see anything. It's just totally dependent on the other person to tell.
the other person doesn't see the ring. That's the beauty. Other person only sees basketball players throwing it, and he can say whether you are throwing like them or not. He doesn't see the ring. If he sees the ring, if he sees the ring, he can tell the person, oh, throw a little to the left, throw a little to the right, throw a little faster or with more force or lesser force. He's not giving those specific instructions. He's simply saying you are not throwing like the basketball player. You are not throwing like the basketball player. You are not. So you are figuring out all those things until finally he feels like saying, oh, maybe you are throwing like the basketball player. He doesn't see the ring. The ring is invisible. The line, like Joey said, the line is a dot to you. A ring is a dot to you.
Yeah.
I feel like this. I mean, these examples are not new. We have sort of all faced it. If you are sitting with your parents or someone when you're young and you're trying to learn something, you can't see what's in their head. They know something in their head and they're trying to tell you. You can't see what's in their head, and you try to write something, then they beat your hand. They say you're wrong. You're right. You keep if they keep beating, eventually you get the correct answer. You learn how to get the correct, but you have never seen what's in their head. You sort of produce answers that they are okay with. They say it's fine.
Just their facial expression, to be
Yeah,
honest.
facial expression, scolding, whatever it is. So the discriminator is them scolding us. That's all. But they are not able to show what's in their head. But eventually, with enough training as generators, we generate the correct answer. I feel like it's exactly that's the analogy.
Right. Okay, so okay, with that in mind, right? So the geometry, the equations, the algorithm, and the code, I think every part of it, I think we have dissected in this class in a couple of hours, right? And notice that they'll in the criterion, you will, in the G loss, you will not include anything of the what is that? Real data, you'll only see the fake data. In the discriminator loss, you'll see both. Okay, and so on. Right? And this optimize. So there are two kinds of loss update that happens. Optimization update that happens. Okay, the first one is here. The second one. So if I keep them side by side like this, I can probably map everything here, right? So this is the discriminator loss whose update is happening here. Okay. And this is the generator loss whose update is happening here, right? Okay, cool. So yeah, you'll watch this recording multiple times if you really want to grok it and play around with the code. We'll share both of them.